Yeah, so Christina, just let me know when you want to start the recording.
Yeah, why don't you start the recording now?
Okay.
You get the and okay, perfect. Okay, I'll start with the introduction then. Well, welcome everyone to the SNAPP seminar. We're really excited to hear Ashish talk today. A couple of reminders in terms of instructions. We are recording the seminar, so if you don't want to show up in the recording, you can just mute yourself or watch the live stream as well. Also, if you have any questions, you're welcome to put the questions, type the questions into the chat box. I'll monitor the chat box, but also I guess Ashish, you can stop and pause for a good time to take questions, and we'll also take questions at the end. Also, I just posting the slides here in the chat box so that you can view them along as well. So today we're really excited to have Ashish Goel speak to us. Ashish is a professor in management science and engineering and also in computer science at Stanford University and a member of Stanford's Institute for Computational and Mathematical Engineering. He received his PhD in computer science from Stanford and was assistant professor of computer science at USC prior to returning to Stanford, and his research interests lie in the design, analysis, and applications of algorithms. Current applications and areas of interest include social networks, participatory democracy, internet commerce, and large-scale data processing. He's received numerous awards, including Alfred P. Sloan Faculty Fellowship, Chairman Faculty Fellowship, an NSF Career Award, and a Rajiv Mawani Mentorship Award. And he was a co-author on the paper that won the Best Paper Award at WWW 2009, an Edelman Laureate in 2014, and a co-winner of the SIG Econ Test of Time Award in 2018. So we're really excited to hear about his work today on sequential deliberation via random walks. And over to you, Ashish.
Thank you. So this talk is mostly old work with some slides which are going to be very familiar to Christina. And so, but the context for much of this is new, and it's only now that I've really understood how this all work fits together. And we do have some new results. And then in this talk, I'm going to focus mostly on providing sort of the high level ideas. Some of the proofs I'm going to just sweep under the rug. But those proofs exist and they're in papers, and I'm also happy to discuss them offline. And before I start, I also want to say, I know this is a difficult time for many people, so the countries which are at war, the countries that are ravaged by the pandemic. Thanks a lot for taking time to come here. And if there's anything I can do to help, please do let me know. So, ultimately, sort of one of the goals in my research group and in sort of among my collaborators has been to facilitate things like participatory democracy, a process which emphasizes the role of citizen involvement in political decision making. So, for example, you can imagine people in a village or a small town getting together and coming up with some collective solutions. So that's sort of one of the things that we would like to facilitate. But what really happens when you try to make any kind of complex decision at scale is that forget about a decision, we can't even get a conversation going. So for example, if you want to vote among two people, let's say Obama or Romney, then of course you can just go ahead and say OR, and that poll proceeds. If you want to make a complex decision, for example, how can we cut the US budget deficit? Then not only it'll be very hard for you to make a decision in a large group, it'll also be very hard to have a conversation in the large group. Right? Someone might say something sort of half reasonable, like increase taxes, and then the conversation will go downhill from there. So the question then is, so for example, if you have this question about what's the ideal way to regulate off-road traffic, then the question is, how can you aggregate unstructured estimates, or when there's no consistent vocabulary for a voter to express their position? So while the budgeting problem sounded complex, they're actually problems which are even more complex, where you can't, where you don't have a formal structured way to sort of present all your solutions. And so the high-level design goals are to incorporate deliberation and negotiation in large-scale decision-making. Try to move away from algorithmic aggregation. For example, not try to do things like let's average everyone's budgets to get a consensus budget. Instead, let's move towards this idea called sovereign aggregation, where the idea is that the aggregation itself is being done by people. And in order to sort of try to escape this assumption of opinions on the line, which has vague social choice, in the sense that a lot of results get proved on the line and they're very nice results on the line, but it's just hard to extend them to other spaces. We would like to design protocols and mechanisms that can reasonably be implemented in practice and that also have good game theoretic properties and provable bounds on the quality of conversation and the outcome of the decision. And we would like to limit the cognitive load on participants by organizing the deliberation/negotiation into small groups and focus on a small set of proposals. So Stanford has a small platform that we have built called the online deliberation platform. And what happens on this platform is that there's a moderator which is automated, and that moderator sort of keeps the discussion, tries to keep the discussion on track using a combination of human cues and AI tools. And at any given time, they're sort of, the platform supports up to 8 to 15 people. Yeah. And it's designed to facilitate a structured and equitable conversation. By structured, I mean there's an agenda with better opportunity for participants to speak up. And this platform has become quite popular recently, and is being used in many online deliberative polls. So, for example, is being used in Japan, Hong Kong, Chile, Canada. In the US, is being used in Baltimore high schools, deliberation in schools, economy and healthcare, shaping at Stanford. So, while this platform is good for having a conversation, it's designed for small group discussions and to have a structured and equitable conversation. It's not clear how you would use this platform to make a decision. So for example, if there are 200 people, you would divide them into groups of 10, and they would go and have 20 different conversations. And they would get a lot of insight would come from these 20 different conversations, but it's not immediately clear how you would convert that into a decision. And we are very far away right now, at least in our understanding, or at least in my understanding, to really solve this problem in practice. So I just want to give you what we can, a snippet of what we can do in practice. I'm going to describe to you some things that we can do in theory. And like Christina said, please feel free to ask questions. In this particular talk, it's okay if I don't finish my slides or if I don't mention all our theorems, but I would like to sort of be able to answer questions or engage people in a conversation. So if you have a question, just post it on chat. And if I can't monitor chat, then hopefully one of the organizers will flag the question.
I can let you know. Oh, sorry. Go ahead. I can monitor the chat for you. Yeah.
Yeah. Thank you. Were people currently seeing my website, the website for the Stanford Center for Deliberative Democracy?
Yes, we can see the website.
Okay. And so now I think I'm going back to the slides. So the important thing here is with this.
We're still seeing the. Oh, okay. Now we're back to the slide.
Thank you. So the key things here are this idea that we're limiting this cognitive load on participants by organizing deliberation into small groups. But then we want to have some theoretical guarantees on the qualities of the decision that comes out. Then we have to somehow find some way to put these small groups into a network so that ultimately we combine the opinions from this group or the dissents from this group with the dissents of that group. And that's going to be the focus of much of this talk. So the model is going to be that users and their ideal decisions are nodes in an unweighted median graph. And this median graph is our sort of attempt at escaping the tyranny of the line, trying to prove results on things which are beyond the line. A median graph is a graph where there's a unique point on the pairwise shortest paths between any three nodes. So examples are lines, because on a line, for example, if you take 3 points on a line, let's say A, B, and C, then the median of these 3 points is actually the unique point that lies on 3 shortest paths, the path from A to C, the path from A to B, and the path from B to C. If you were to take a tree, and let's say these points are A, B, C on a tree, then there's a unique point. You find the unique path from A to B on the line, the unique path from A to C on the line, and B to C on the line, and they'll all meet at one point. And so it's not that hard to see that high dimensional spaces with the L1 norm, hypercubes all have this property. So if you prove results for the median graph, you're proving them for something slightly more general than the line. In fact, much more general than the line is dVW, which is the shortest path from V to W in G. Okay? So if this is the ideal point for A, and if C gets chosen, then the unhappiness of A is going to just be the length of the shortest path. And this median graph is not known to the mechanism designer. This is just an artifact for the analysis. So we're not allowed to do any algorithmic aggregation. We're not allowed to say, let's just collect the ideal opinions for A, B, and C, and let's do some computation to actually find this median point. And so again, like I said, if you have any questions about the motivation, about anything philosophical about the model, please feel free to ask at any point in the chat. So for any point X in the median graph, we define this big D of X as the sum of the distances of X from all the users. And our goal is to find X star, which is the argmin of dx. Okay. And the distortion of a point X is this dx over dx star. So the sum of the distances to X divided by the sum of the distances to the optimum point. Okay. And by now, this is well enough understood. There is a survey on this, a very nice survey on this by Anshilevich et al. Just from this year. So here's some sort of high-level known results in this model. Randomized dictator has expected distortion 2 for general metric spaces. So for example, if you just pick a random node V and say, well, V, what do you want? And implement that solution, it'll have an expected distortion of 2, not just for median graphs, but for any underlying metric space. There exists deterministic voting mechanisms with distortion 3 for general metric spaces. And any Condorcet consistent voting rule, for example, Copeland's rule, will give the optimum solution for median graphs. Now, I know that without sort of a big background in social choice, these last 2 results it might not be immediately clear what these last 2 results mean. But in any case, these last 2 voting rules require a full ranking of the points, which is not aligned with the goals of this talk. So we're going to really sort of focus on the first one and take that as our benchmark. The randomized dictator has expected distortion 2 for general metric spaces. And so if we're going all the way to median spaces, we at least want to do better than 2. So if we're doing worse than 2 in distortion, then that's not a very useful result, especially because all the algorithms that we see in this talk are going to be randomized. Okay. So for the talk outline, first we're going to assume that the median graph is fully occupied with users. We get very strong results, but this is a weaker model, and it's not clear how to implement this model in real life. Okay. Then we're going to assume that the median graph is not fully occupied. It's a very strong model and corresponds to a practical design. In fact, I'll show you like a small demo about how this idea could sort of be actually applied in practice, but it has weaker results. And so that clearly leads directly to sort of open problems, which is, can we get the stronger results and a stronger model at the same time? I'm going to point out some connections with participatory budgeting, and I'm going to describe open problems as sort of at a fairly high level. So some of the lower level open problems are going to be clear, like can you improve this constant? Okay. Some of the open problems are broader, which I'm going to focus more on. So the first paper is with David Lee. It's several years old, but I think this whole way of thinking about this and connecting it to real platforms is new. So, which is why I think it's worth talking about. So the idea here is to go beyond voting, and we want to go beyond voting by having these small group interactions. So in particular, it's very hard to design good interactions between just two people. Okay. So for example, if just to take one person on my screen, if Nelly and I disagree on something, we don't really have any normative basis for deciding whether I am correct or she is correct. Right? There's no grounding, there's no anchoring, which tells us whether we should go with my idea or Nelly's idea. Right? And so triads are sort of the smallest group. 3 people are the smallest group, where you can imagine the third person providing the anchoring, which then Nelly and I can use to sort of decide which of us is correct on a particular issue. And some of this can be formalized, as I'll mention later. So we're going to assume that we are doing triadic interaction. And in particular, for the first, for most of this part of the talk, I'm going to assume that triads can just find their one median. Okay. So there's some kind of a magic box by which if 3 people interact, there's some voting mechanism, some game theoretic mechanism by which these triads will come up and say, well, this is our one median. Okay. And the one median of 3 points, once again, especially because we're talking about median spaces, is going to be this unique point which lies on all 3 shortest paths. That's what we are defining as the one median. That's also the one median if we just follow the technical definition of a median. Okay. And so on the line, this becomes very simple. If each member just votes among the other 2, then the person who gets more votes is going to be this one median. So that's what we're going to assume. And so based on this idea, I'm going to build this process that we call triadic consensus. So imagine we have a bunch of participants. Okay. All these participants, imagine they're represented by a color, and imagine we have a big urn where we put all these participants. Okay. And then we're going to repeatedly pick 3 participants from this urn and replace these 3 participants by 3 copies of their one median. So let's say we end up picking these 3 points. Let's assume that the underlying metric space is this tree that's given to us up here. So let's say these 3 points lie in this tree. And let's further assume that this tree is not known to the mechanism designer, but these individuals can actually find their one median. So in this particular case, the one median ends up being this yellow point right here, because it's on these 3 shortest paths. Okay. And so what we'll end up doing is we'll end up replacing these 3 points in the urn. We already took these 3 points out of the urn. We're going to just replace them with 3 copies of this yellow node. And so that's what our urn looks like now. And we'll keep repeating this process. And we'll keep repeating this process till everything in the urn is of exactly one size. And we have results which show that at least for median graphs, this is going to ultimately happen. Okay. And so winner is whichever color remains. Once most of the nodes are of one color, you can safely assume that that color is going to actually end up winning. Okay. So here's like a small, yeah. So Nelly has a question which is, does the result then depend on a lot on the order in which you choose the nodes? So it is a randomized algorithm. So the result does depend somewhat on the order in which you choose the nodes. But we have a high probability result that regardless of the order, with very high probability, not regardless of the order, we'll actually find something which is very close to optimum. So in particular, for example, if you have a binary tree, okay, and in this binary tree, let's say the height of the binary tree is 1 million. Okay. So the winner is chosen, you would assume that you could imagine the winner is chosen from like the top 500,000 levels, which would actually mean that the winner is one of the top square root n nodes closest to the median. The median, the optimum solution here is just the root of the tree. Okay. Or you could imagine like that the winner is chosen from the top 1,000 levels, which should be like the square root of the depth of the tree. Or if you say like 20 levels, which is like the log of the depth of the tree. But in this particular case, in fact, with overwhelming probability, the winner will be one of the top 3 nodes. Okay? And so, of course, like it's a randomized algorithm. So strange things can happen with small probability. But with overwhelming probability, the winner will be one of the top 3 nodes, either the root or one of his 2 children. So similarly, for a square grid, let's say you have a million by million grid, with very high probability, the winner will be in the center 3 by 3 square. Okay. So again, you can imagine like the center 500 by 500 square would have given you something like in the top 1/4 of the nodes. And once again, the median or the optimum solution we're looking for in this case is the center of the square. Okay. Something like b equal to 1,000 would have given us the square root of the number of nodes, but we actually will end up getting just 3. So the winner will be in a 3 by 3 square, which is at the center. And so why would this happen? And because I said we want to escape the tyranny of the line, I'm going to illustrate this on something slightly more general, which is a tree. And again, I'm not going to give a full proof, just give you like an idea into how this analysis might happen. So let's imagine, for example, that right now we are concerned with whether the winner ends up lying on this side of this line, this thick yellow line, or that side of the thick yellow line. And let's assume that the underlying space is a tree. Okay. So let's just make these simplifying assumptions. And in fact, as you can imagine, because it's a tree, if we can figure out the probabilities of the winner lying on every side of on both sides of every line, then we essentially can easily determine the probability of the winner lying at any particular node, right? By just repeatedly applying this argument to line after line after line. Okay. So if we're only concerned with the winner lying on this side of the line or that side of the line, then you might as well color all nodes on one side red and all nodes on the other side blue. And this median thing is going to have a property that if you pick up all 3 nodes, which are red, then the median is going to be red. If you pick up all 3 nodes which are blue, then the median is going to be blue. And if you end up picking 2 blue nodes or 2 red nodes, then the median is again going to be blue and red respectively. So for example, if I pick this node, and that red node as my 3 participants in a triadic interaction, then because the shortest path between these 2 nodes is entirely blue, the winner is going to be some blue node. So with that in mind, we can get a fairly simple random walk. Let's think of a random walk on a line where this number 3 represents the number of points which are currently red in our urn. And we're trying to figure out how this random walk moves. In any step, if we pick all 3 red nodes, then the random walk will remain, or all 3 blue nodes, the random walk will remain where it is. If we pick 2 blue nodes, the random walk will move to the left, so we'll go to 2. If we pick 2 red nodes, the random walk will go to 4. Okay? And so this whole process on this tree now reduces the simple random walk. Okay? And the argument for the full triadic graph is much more complex, but essentially follows a very similar idea. Okay. So with these 3 points, let's say we choose these 3 points. Okay. And so if you think of any particular point on this line, let's think of being at point I on this line, then the probability that we're going to move left, if we choose 2 nodes which are red, which happens with probability I over n squared roughly, and 1 node which is blue, which is n minus I over n. And we're going to move right if we choose 1 node which is red and 2 nodes which are blue. So this just becomes a simple random walk on the line. And observe that there's a quadratic term in this random walk evolution equation. And because there's a quadratic term, whichever side, the ratio of the 2 probabilities is just going to be the ratio of the 2 sides. And that makes this random walk sufficiently unbalanced that is if you start anywhere close to the center, it's going to ultimately, then it can sort of go anywhere. If you start anywhere off center, then the random walk is very likely to get absorbed on the left, so on the side where you start. And that means that even a slight disbalance in the size of the two groups will lead to this random walk overwhelmingly favor the larger group. And that gives us a hook by which we can apply these probabilistic bounds repeatedly and come up with very strong results about where the ultimate solution is going to come from. So in particular, this is just sort of how you would apply the random walk iteratively. Again, I'm not going to focus on the details, but what you can show is for any median graph, triadic consensus finds a 1 plus order square root log n over n approximate one median. Okay? So distortion is going to be 1 plus square root log n over n, which is really small. It's much better than having a constant distortion. It's much better than a peta style result, where it's 1 plus epsilon for arbitrarily small n. Arbitrarily small epsilon is actually 1 plus small o of n. Okay? And just to remind you, a median graph is a graph where for any three nodes A, B, C, there's a unique node X that lies on the pairwise shortest path between A, B, and C. Okay? And note, we also prove lower bounds showing that we need at least three nodes in a scheme of this type. So we couldn't just have done like dyadic interactions in this setting. The actual details of the magic box, what happens, how people find the median, are sort of beyond the scope of this talk. But basically, we ask questions of the form, what proposer is closest to X in between Y and Z? And we put a small game theoretic mechanism on top of this. Yeah. So because this is a game, you can think of a strategic equilibrium. In the strategic equilibrium, we're going to make the assumption that participants are not strategic in declaring their positions, or their positions are known to everyone, but participants can be strategic while participating in a triad. Okay. And we realize that this assumption is somewhat unreasonable. If participants can be strategic while participating in a triad, then maybe they should also be strategic in declaring their position. But I'm not going to dwell on this modeling inconsistency, because we have a bigger modeling inconsistency implicit in this result. And so the strategy space then becomes the votes cast in any triadic interaction. Like in a triadic interaction, who do I vote for? And truthful voting, in this case, turns out to be a subgame perfect Nash equilibrium in this entire extensive form game. It's an extensive form game because you're doing multiple triadic interactions. There's some complex process that determines who gets chosen and then gets to play in the next round. Okay? But these subgame perfect Nash equilibria are about as strong a result as you would generally get in an extensive form game. So it converges fast. It converges to a point which is with very high probability really close to equilibrium. Okay, and has very good strategic properties. So it might, on the one hand, it might seem like we are done because you have a really strong result. And when we came up with these results, I think this was with my X2 and David Lee. When we came up with this result, I really thought like, okay, we are now done with this problem because the results are just so strong. But in hindsight, there's some modeling assumptions here which are not internally consistent and which need to be fixed. I think that's what that's sort of what leads to me describing this paper in this talk, right? And so again, we assume that the entire median graph is filled with users. Okay? So we assume that every opinion on the median graph has an easily identified representative. Okay? And that seems like something that may not happen in real life, right? In real life, for example, even on the line, there might be solutions which lie between two nodes. They might not be, it's not obvious that you can find for every possible decision that you could make, you'll find there'll be some easily identified representative. And we further assume that this space is sufficiently complex that just ranking all the alternatives is not an option, right? So we're not asking each participant to just come and say, okay, well, here I'll take these 20 alternatives or 200 alternatives or 2,000 or 2 million alternatives and just rank them. Okay? We also assume the space is sufficiently unknown to us that we can't do algorithmic aggregation. And yet we assume that a user can answer queries like find the point that's closest to X on the line between Y and Z. Okay? And so again, I don't undersell this result either, because this result, the proofs are very strong, and they're very, it's surprising that for something as complex as median graphs, we can get convergence, strategic, good strategy proofness, and we can get this result of near optimality. But on the other hand, if we want to translate these results into practice, then we have to remove some of these modeling assumptions, because we would like to sort of use ideas from this triadic consensus to actually affect how large-scale decisions get made. And in fact, that's the process by which I realized that there's some modeling assumptions here that we would like to address, because that's when I got into collaboration with political scientists, and we started to put together this deliberation platform that I described before. We realized that it's not clear how we could take this triadic consensus idea and directly implement it. And so this clearly needs some work. Okay? And it's an important open direction, especially since we have a lot of room between nearly optimal, which is our results, and distortion 2, which is random dictator, which is the sort of best known in general for problems of this type. We'll provide one such approach next, which is sequential deliberation. In this approach, we will not assume that the entire median graph is filled with users, or that people can easily find this median and find who represents this median. But before I move on, I would like to maybe stop and take questions for a couple of minutes. If there are any questions. If not, I'm happy to move on. So I don't know whether I should call on people or the organizers, but yeah, Varun, go ahead.
Can I ask a question? Sorry. Sorry, this is Xiaojun from Purdue. My question is, you replace like every 3 nodes replaced by another node, right? And then you pick 3 again. But how do you, in practice, how do you ensure that the one that you pick will, represent the opinion of the middle one? Does that make sense?
So this is just a theory result, and I think that's one of the problems in our argument. So, for example, what happened? I'm sorry, it looks like my presentation stopped. Can you still see my screen?
Yes.
Okay. So we assume that participants are not strategic in declaring their positions, or their positions are known to everyone. Okay. And so we just assume this problem away. And I know this is not optimum, but like I already said, some of the modeling choice, while this result is very strong, some of the modeling choices don't really correspond to how things will happen in practice. And this is exactly the difficulty that we ran into when we started to think about actually implementing this in practice. So our initial goal was to take the deliberation platform that I described and build it around something like triadic consensus. So I know I didn't give a satisfactory answer or a question to the answer that's satisfactory, but I hope I.
Thank you. But do you envision some kind of fix down the road, or any?
Yes, absolutely. I think in the next, but I mean, everything is a trade-off. If someone comes up with a result that's as strong as this result, right, and is actually truly strategy proof and does not have some of these slide modeling mismatches, that would be really impressive.
Okay.
But I think even addressing them, even with some more distortion, like we get distortion 1 plus small o of 1. If someone can prove these something which will result 1.05, 1.1, I think that would also be really exciting. And I'm very optimistic. Once you start to sort of go to distortion more than 1, I'm very optimistic.
Okay. Thank you.
Actually, I had one clarification question on subgame perfection. So this is an expectation, or like even if I tell you which triads will get picked deterministically, even then it's subgame perfect?
It's subgame perfect even if you know which triads are going to get picked. Because these, giving a question, I'm assuming that you know that these results are very hard to prove in Bayesian settings or in stochastic settings. So actually, we prove this for every instantiation of the random choice.
Right, makes sense. Thanks.
So, quick question about the relation between your result and the distortion results. Can I interpret your result as saying that if people are located uniformly on the graph, then you end up getting something like distortion 1, but in the worst case, you get distortion 2? So, like, can I think of like occupying different spots of the graph as essentially a sort of skewed distribution, which is far from uniform?
No, I think so. This it's not clear how to run this method if people are not represented by their. Oh, sorry. So you could imagine this purely as a protocol that's running on a computer as opposed to by human beings, and you could randomly pick 3 individuals and replace them by their median. No, I don't think we'll get those results, because I think for 3, if the underlying space is not a median space, then it will not. Oh, sorry, you mean for a median space? Do you say, like, if you assume there's a median?
For a median space, yeah.
Yes.
So I was just
For a
thinking
median
first
space,
have a space and then sample points on the space from a distribution.
For a median space, if you're doing it algorithmically and you just repeatedly pick 3 points and replace them by the median, then you will get the same optimum solution. And if you say that you're picking 3 people uniformly at random, and then within each triad you run the following algorithm, where you say, okay, I'm going to ask X to vote between Y and Z, Y to vote between X and Z, and Z to vote between X and Y, which is the only natural way of choosing among these 3 people, and then pick whoever gets 2 votes. Then you can show that this method empirically has very good properties, but we have not been able to prove formal results. I think this last question is what you're asking.
Yeah, I was just sort of trying to see if there's like a model. Maybe you'll talk about it in open questions, but like, is there a model sort of interpolating between yours and the kind of the Anshulevich style results? As that there's a sort of continuum of
empirically, I think the thing that you're hinting at works very well. But formally, we haven't done anything, either factor 2 or better.
Yeah, thanks.
Okay. Should I go ahead or?
Yeah, you can go ahead.
Okay. So here's the kind of thing that we would like to sort of get towards. So ideally, the first thing we would like to do is we would like to get away from this idea of even having 3 participants in a conversation. Because when you try to implement something like this, even getting 3 people to agree on something ends up being a complex decision-making process. Ideally, we like to have just 2 people. And we like to have the third person being present in proxy via their decision, but not actually take part in the process. So one example of that is doing something like Nash bargaining. So what happens in Nash bargaining is you might give people an outside alternative and then ask them to make a decision given that outside alternative. And if they agree, then whatever they agree on becomes a new alternative, becomes a new decision. Otherwise, the old decision stands. So here's an example. Right now, I'm going to just interact with a bot. So imagine that there's a question being asked, which is, how can we improve Stanford? And it's a very unstructured question. We want to sort of have a deliberation about this question. And let's imagine I get paired up with a random partner. And for this random partner, we are given a current statement of how one might improve Stanford. So for example, there might be, you might increase faculty research funds, more travel support for PhDs, more benefit for admins. Do people see the screen with this?
Yes, we can see.
So you can easily imagine a situation where I just edit the statement and I say, well, more benefits for admins. Why not make it more benefits for admins and faculty? Okay. And I'll say, okay, this is my proposal. Okay. But my proposal is not going to the person who made this argument to begin with. Okay. This suggestion came from some third party who's not in the room. I'm in the room with my partner, and I'm editing the decision made by this third party and proposing it to my partner. So I propose it to my partner. My partner says, okay, my partner is just a bot, so he's just playing a script. I like your change, but I would like to add one more point. How about this? Okay? And the partner says we should be good to each other. I can reject my partner's changes or I can accept them. If I accept them, then the new thing that the 2 of us agreed on becomes the new decision. Okay. And so as you can see, the way this particular demo is structured is that you can just change the question and the process remains pretty much the same. So you can apply the same idea to in very general settings. So that's the intuition behind. So this demo is sort of the intuition behind the formal results that I'm going to present next. Sorry, I should have asked questions while I was loading up my next presentation. Does anyone have any other questions while I'm loading up my next slides?
Have you guys thought about using any of these ideas for talking about like program committee decisions for papers and stuff like that?
No, and I think that's like a little bit deeper conversation question, but I'm glad you asked it. So what we're going to describe next is something which is going to be like horse trading. It's like negotiation. You're given an outside alternative, and then two of us, let's say, again, picking up the person next who I see, say Daniel and I are going to do some deliberation. What we're really doing is trying to do horse trading with each other to figure out like how should we compromise with each other. Now, a lot of the deliberations, ideally, you would like to have a deliberation that is this property that you would call Habermasian. I'm going to try this in a chat. And a Habermasian argument is one that is like the unforced force of the better argument. So ideally, you would like things like program committees to work not by sort of saying, okay, this is what Marty thought, and now Vivek and Ashish happen to be in the room, so how can like Vivek and I horse trade to improve Marty's decision, right? What we'd like to do is to actually, often what happens in a true deliberation is that I might say something that actually shapes your opinion, it changes your objective function. That's what true deliberation is, right? It's not about sort of me and you negotiating with each other. And it'd be great to have program committees sort of try to approach this Habermasian ideal, but that's not what our theory results do. So that's what we haven't tried to do it. Now, the deliberation platform that I showed you, that achieves this Habermasian ideal, primarily because it's meant to mimic a process called deliberative polling, which is based on this idea. But then that process does not actually produce a decision. So I think the social choice for a long time was just mired in voting, like how do you vote? But really sort of when people make decisions, they don't just vote, they horse trade, they shape each other's opinions. Someone telling me their story shapes my opinion of what the world looks like. Someone telling me my story in a different way might also sort of change my perspective on how to optimize my own decision objective. And so ultimately a goal, and by R, I mean like a community goal. It should be a community goal because there's no way one research group can do it. Should we take these theories of sort of these very mathematical theories of negotiation, opinion formation, and take these very sort of practical but broad platforms of the type that we are building and somehow have like a unified theory and a unified platform? I don't know whether I answered your question, but please feel free to sort of ask a follow-on if I didn't.
No, this is interesting. Thanks.
So what do people see now? Do they see a slide saying sequential deliberation?
Sequential deliberation.
And sequential deliberation is basically going to be the idea that I described before, just now. So I'm going to go through this quickly. Let's assume you're given a set of agents. They start with an initial solution as 0. For example, this initial solution could be the ideal point of a random agent. Then for rounds going from t equal to 1, 2, all the way up to infinity, at time t, we pick 2 agents uniformly at random from these n agents. And let's say st is a current solution. We start with S0, and every time at time step t, let's say st is a current solution. So I should have started time at 0, but let's ignore that for a second. And these two agents bargain with this ST as the outside alternative. Okay? And if they agree, then the agreement point becomes the new solution. Otherwise, the old solution becomes a new solution. And this gives some kind of a random walk. The random walk is over these current solutions. As at every step, we pick two people uniformly at random, which are going to change this current solution. And so we are going to analyze the expected distortion of the stationary distribution of this process of the S's. So in this particular case, we're not going to have any notion of convergence. We just keep running this process forever, and we look at the stationary distribution. Which in most of the audiences, I have to justify that, but hopefully in this seminar, people will let it pass. Okay. So now we're going to assume when they bargain, we're going to assume they do Nash bargaining, which is axiomatic support, and is equivalent to maximizing the product of the improvements for the two participants. Okay. This is what it looks like. So imagine that you're given, imagine the square is sort of the underlying metric space on which opinions lie. This point here, which is labeled the disagreement alternative, is blue, but not everyone can see colors the same way. So the thing labeled the disagreement alternative is what's given to them. That's the ST. Alice and Bob are the UT and the VT. Okay. And sort of, we're assuming that Alice knows the distance from herself to every point, and Bob knows the distance from himself to every point. Now, each of them can sort of choose to champion one thing. So Alice can say, well, I really want the red point. And Bob can say, no, I really want the green point. And if Alice says, I really want the blue point, and Bob says, I really want the green point, that means that they're voting for this point. Okay. Now, at this point, they haven't agreed. So the disagreement alternative remains the chosen solution. And what Alice and Bob get is what they were getting before, which is 2 and 1. Okay. If on the other end they agree, for example, if they agree both on the yellow point, then the yellow point becomes the new solution. Alice gets 1 and Bob gets 2. Okay. And in fact, the right thing here would be to choose this green point, which is actually Bob, in which case Alice gets 1 and Bob gets 0. Remember, smaller numbers are good because you're measuring distances which correspond to unhappiness. Okay. So, if Alice and Bob were to do bargaining, they'll actually end up choosing the green point, and that's basically Nash bargaining. Okay. So here are results, and I'm going to give very quick intuition about these results. Yeah. On median graphs, Nash bargaining between agents U and V with ideal points PU and PV using disagreement outcome S finds the median of PU PVS. So this third person, even though we are doing dyadic interactions now, U and V are the ones who are negotiating. This third person who proposed S is very much in the room, or the group that proposed S is very much in the room, because you and me are doing Nash bargaining with this third thing as the outside alternative, we actually end up finding the median of these 3 points. We can analytically compute bounds and approximating the social cost minimizer by embedding onto the hypercube. All agents bargaining truthfully representing their ideal point is a subgame perfect Nash equilibrium of the extensive form game defined by sequential bargaining. So right now we are fixing all the modeling assumptions of the previous talk. I know this the strange strategic behavior was a cause for concern, but of course we're going to give up in terms of the bounds that we can obtain. Yeah. And the chosen alternative converges to a stationary distribution in order 1 steps. Okay, so it's like we are proving properties of stationary distributions, but it converges very quickly. Okay. And these results hold for general median graphs, but just for this talk, I'm going to illustrate them on a line. Okay. So for example, on median graphs, for the first result, the Nash bargain between agents U and V with disagreement S finds a median of PU, PV, and PS. Okay. So first, if S lies between PU and PV, then there's no Pareto improvement over S as far as U and V are concerned. If you move towards U, then V is unhappy. If you move towards V, then U is unhappy, and they're never going to agree on anything other than S. Since the Nash bargaining point is just going to be S. For the result of the Nash bargaining solution must lie between PU and PV, as there's a strict Pareto improvement. Okay. And any Nash bargaining solution has to be Pareto optimal. So we are basically left with this solution, this third situation, where we're going to assume that S is less than PU less than PV. I mean, without loss of generality. And let's assume the Nash bargaining point is this point in the middle, which is X plus PU. Yeah. So if you think about it a little bit, then if we choose this point B, then PU was earlier at a distance D and is now at a distance X. So PU gets an improvement of D minus X. And PV gets an improvement of D plus X because B is like this D plus X closer to PV. So you're trying to maximize D minus X times D plus X, which is clearly maximized when X is 0. So B actually has to just lie with PU. Okay. So in all cases, you can show that the median is actually the solution that you'll end up finding. And somewhat surprisingly, that ends up being true even in median graphs for Nash bargaining. Then we can analytically compute bounds and approximating the social cause minimizer by embedding into the hypercube. And again, I'm not going to show how these bounds are computed. I'm going to just give you an intuition on sort of what the process for doing it is by just describing a simple random walk that you could use, for example. So you assume that the endpoints on the line. If the current solution is xi, then the next solution will be xi if we choose 1 point from each side of xi, because then xi itself will be the median. The next solution will be at least xj, where j is bigger than I, if we choose both points to be at least as large as xj. Okay. And there'll be at most xj, where j is less than I, if we choose both points to be at most as large as xj. And this ends up being a Markov chain or a random walk, which is only slightly more complex than the one that we saw in the previous part of the talk. And so we can actually formally analyze it. And so we explicitly analyze this for the line, and we managed to bound it, get a good bound for all the median graphs. And then the other intuition on the line was that the chosen alternative converges to a stationary distribution in order 1 steps. So let's assume, let's consider 2 consecutive steps, and we condition the subsequent random walk after these 2 steps. So we're going to do these 2 steps, and the subsequent walk is conditioned on A, B, C, and D being the 4 participants chosen in these steps, where A is less than B, less than C, less than D. Okay. And so if it turns out that A and B are chosen in the first step, then the solution that remains at the end of the 2 steps will be C. Okay. Because imagine that A and B are chosen in the first step. We condition on A, B, C, and D being the 4 participants, but not which ones are chosen in the first step and which ones are chosen in the second step. If A and B are chosen in the first step, then the outcome out of the first step by the previous slide has to lie between somewhere in this range. Okay. But no matter where in this range it lies, in the next step when C and D negotiate, C will get chosen. Okay. So it doesn't really matter what the previous history was. The history gets forgotten. And similarly, if we end up choosing C and D first, then B is going to be the outcome, regardless of what the solution was at the beginning of the 2 steps. And that means that if we remove the conditioning, because it didn't really depend on A, B, C, and D, all dependence on the past is lost with probability 1/3 in 2 rounds, which means this process converges in order 1 steps, which means you just need to run this kind of deliberation for a few steps. Here are bounds for the median spaces, for the median space. We can show that our process has an upper bound of 1.208. So our distortion is like 21% at most, which is much better than random dictatorship. We have lower bound of around like 12.5%. And then the expected square cost, which let's say you want to measure some kind of like the second moment of the cost and not just the first moment, because you want to somehow bound the worst scenario or want to bound outliers. Then random dictatorship actually has infinite cost, where sequential deliberation still has cost 3. And this result is interesting because this is qualitatively different from random dictatorship, not just quantitatively better. And then Fain et al. Has shown that even simpler single node mechanisms also have good performance. And so So like I mentioned before, this result suffers from fewer modeling assumptions, or there are fewer modeling inconsistencies, but then the result is, of course, an approximation result. Okay. Now, in terms of trying to apply this to practice and connect it to some of the work we are doing, we have a platform for participatory budgeting that I've inflicted on people in some of the people in this audience many times. I'm not going to show it to you. What happens in participatory budgeting, at least in the US, is that a set of proposed spending projects get put to the ballot for residents directly, subject to a budget. And there are many approaches for ballot design and aggregation. For example, knapsack voting, approval voting, distortion minimization, utility elicitation. But however, most work, with this exception of computational results by Talman et al., does not consider project interaction. So what if two projects are substitutes for each other? Okay. So I could build a parking lot on the east side of campus or the west side of campus. Okay. Or they're complements. So for example, I want to run a shuttle from Stanford to the train station, and I want to give people free train passes. Okay. Or they're contradictions, like these two things cannot happen at the same time. And that would be like, I want to build a parking lot in this space, or I want to build a park in this space. And all the ballot designs that we have been a part of don't sort of take these rich project interactions into account. And so, but you can simply prove that if voters were to understand project interactions, let's say I don't understand these project interactions, but voters do. And if we further assume that two interacting projects can be either perfect complements or perfect substitutes, then you can show that sequential deliberation with the interacting projects is the same as sequential deliberation without project interactions. Because once people understand these project interactions, they can map them into some underlying space where these interactions essentially wash out. Okay. And so we have recently shown that single round triadic deliberation has distortion less than 2 for participatory budgeting. There's a large gap between the lower bound, which is like 1.3 something, and upper bound, which is 1.9 something. And this participatory budgeting space, the space in which budgets lie, ends up not being a median graph. So this is an example of how results can extend beyond median graphs. In terms of directions, they can be a direct extension of our results. Just going beyond median spaces is stronger results of participatory budgeting, analyze larger groups, maybe improve our bounds. But they can also be axiomatic approaches to group deliberation, which I think could be quite exciting. Just like the axiomatic approaches to Nash bargaining. There could be models and mechanisms that take true deliberation into account, not just horse trading, which is basically what Nash bargaining is. And then implementations. I feel like our theory understanding and our practice understanding is somehow, it's sort of like we're all circling around I get this feeling we're circling around some common point where everything is going to come together and look very obvious in hindsight. But it's eluded us. And I definitely feel like finding these models, mechanisms, algorithms, implementations, axioms is definitely going to be a community effort, because definitely beyond any one group. I'm sorry I'm running, I didn't leave that much time for questions. I'm going to stop here.
I'll clap on behalf of everyone. And
I'm sorry, I can't hear you. I don't know whether it's just me or other people can't hear you either.
Hear me now? Or maybe not. Let's see. Okay, can you hear me now?
Yes.
Yeah, I just say thanks for the great talk, and we'll just open the floor for questions. Sure, Varun, you had your hand up earlier. Did you want to ask what?
Applauding.
Oh, okay, that's right. Yeah, Phil, so feel free that anyone can jump in with questions.
So I guess an obvious thing about the first part, which you all would have seen, that even though you're saying you're getting a 1 over square root m convergence, if you replicate people a certain number of times, or just give them a set of tokens, you can get any arbitrary convergence. So I mean, given the other work you've done, I mean, I was just wondering, like, what are your thoughts on the idea of like using tokens in these mechanisms, and like how much more you can get if you give people multiple tries to do things? You're muted, by the way. Oh, sorry. Ashish, you're muted.
Yeah, thanks for pointing that out. Yeah, that's actually very true. So I think you could you could give everyone a bunch of tokens to begin with, and then as they're using up these tokens, when someone gets chosen as the median, they collect 3 tokens from the 3 participants, and then you can show with the high probability you will actually converge to the actual optimum in many cases, but then the convergence time increases. In this second one, I don't actually think this result is, in the second one, I don't think the results are going to change as stated, because we are drawing them from this distribution. But I think you're pointing to something deeper. I think what you're saying is, if we give people tokens and we'll somehow let them use these tokens to buy influence or trade influence. Is that the kind of thing you're hinting at?
Yeah, I mean, like, what are your thoughts on what's the power of that? So, like, what's the power of people sort of trading with tokens versus just taking like one decision?
So, in terms of the Habermasian ideal, I don't know. Because the idea behind the Habermasian ideal is you don't amass influence. So that would go towards something like liquid democracy. And I think it's a very, very useful and interesting idea, and deserves analysis and also deserves implementations. But my main collaborator on this deliberation side is Jim Fishkin. And he would be aghast at the idea of people amassing influence in the form of these tokens and trading these tokens. You know, say if you have something to say, then say it. And if it's good, then let people believe it. And so he would be very upset by this idea. Now, as a theory mechanism, I think it's indeed fascinating. If you could somehow, so for example, even though the results here are very couched in the notion of some economics in the sense of having strategic behavior, they're not really markets. And can you actually build like some kind of a market into this this kind of a mechanism? I think it's a fascinating direction. I hadn't thought about it. I think about markets in a sort of more like much more structured settings. Like you're choosing between these. For every alternative, you're choosing yes or no, yes or no, yes or no, and you can make a market by which people can trade influence. But in something as unstructured as we're just making a decision, I hadn't thought of a market-based approach, but it sounds like a very promising direction.
I had a question on the second thing, which maybe also touches upon Sid's point, which is like, so right now in the second model, you assume that there is this outside option, which somehow was agreed upon by consensus and of the history, but like 2 people can sort of by themselves just completely change it. But if you imagine there's a weight of consensus on that and you sort of don't want to change it, like would it sort of get you closer to like these distributed consensus algorithms or distributed averaging kind of algorithms and maybe better guarantees?
So the question is, so I think there are 2 separate issues here. One is how can you avoid this thing where just 2 people can override the group decision. So the last 2 people end up being somehow outliers, then the whole decision gets skewed. So I think that's just this whole stationary distribution is just the theory result. The way we are hoping to use this in practice is the following. So for example, imagine you have a small group discussion, and then at the end of this discussion, people have to perform a task. And right now, the task that people are asked to perform after they've had this Habermasian conversation is what are 2 questions whose answers will still clarify their thinking. So what we're imagining is that these 10 people were engaged in some kind of deliberation of the type that I described in sequential deliberation. And at the end, we'll take their ideas and put them to a vote. Or you can imagine starting not with one solution, but starting with a whole basket of solutions. So instead of starting with one solution as 0, you ask everyone for the ideal point. And so you start with a whole basket of solutions. And repeatedly, you're picking one solution from that basket and replacing it. And you can show that the same properties hold there, but then hopefully the entire basket will converge to a stationary distribution. So you'll have not just one point, but a whole station distribution where the outliers would be just one solution. Did I answer your question?
Yeah, that makes sense.
Ashish, I was curious if there's a model that would capture, like I guess in the current models, like there's no benefit to having the smaller deliberations being larger than 3. But I feel like, will that make it kind of take a long time to converge? Because I think I don't know, I just feel like if you have a very large group, by just doing it 3 by 3 by 3, would it just like have to have people, have to participate in a lot of conversations? I don't know if there's a way to capture a model where you actually get gains from like having larger groups in the aggregation kind of process.
I think that there's a view of this kind of social choice or deliberation on the behavioral side as sort of learning, where you say that the reason my opinions are changing is because someone has shown me a point which I didn't know existed, or someone has told me an anecdote which I didn't know existed. And I feel like the reason we get strong results with small groups and we're not really able to use large groups in any nice way is because we don't have models of that type yet. And I think a model where your opinion is changing or conversation is progressing via new ideas being injected into the mix into the mix. I think that's where we'll start to see somehow a trade-off between group sizes where some things improve and some things don't go well. I know I didn't answer your question very precisely. I don't actually know the right answer. This is just my intuition.
Thanks.
Yeah, I guess I had a question sort of along those lines in that, do you have like any like preliminary ideas of how to capture sort of the exploratory nature of true deliberation?
So there's I mean, we have lots of, we have tried lots of models. I can hazard, I can tell you what we are thinking about now, and maybe you will have more luck with it than we did so far. So, for example, you can imagine that conversation proceeds by arguments. And there's a theory of argumentation. But it's not clear what argument convinces anybody else. So let's try to sort of achieve this Habermasian ideal and say if an argument is made, then no matter who makes it, it will convince people. But let's say it won't convince everybody. So then you're saying that an argument is Habermasian for this set of people, because that set of people will see its value. And this other set of people, their value system is so different that they're not going to see the value. So I think the thing that we are hoping to build some kind of a model around is that there's some structured set of arguments which people can make. But an argument is only convincing to one set of people. And I think that's the direction to go. Now, there's been a lot of study of this kind of argumentation, which is the same criticism that I was making about this idea of unless I analyze opinions on a line. That people assume that these arguments are convincing to everybody. And then you get this very strategic game about what order do you present arguments in, because people will forget the previous argument when they see the new one. So there are these models and these results which say whose titles and abstracts sound like they're doing the right thing, but I really feel like they haven't. I really feel like we're not yet there.
Thank you.
I know it's a SNAPP seminar. I'm sorry I didn't do any of the random walkthroughs. Okay. Thank you very much, Christina. Christina, it's very nice to see your.
Thanks, Ashish.
Your baby.
This is Esther. Hi.
Hello, Esther.
She's a little tired. She missed her morning nap. So thank you, Ashish, for a great talk.
Thank you, everybody.
Thank you, Ashish, for the talk.
Bye-bye.